So in this last video, we're going to talk about a half-life and how we use exponential functions and logarithm functions to solve real-world problems. Okay, so here's the formula. I'll just start with that. There's the formula, and I'm going to show you where it comes from. But half-life is when we're talking about radioactive material and the material is going to decay. So you have like 500 grams, and after so much time, you only have half of that. So you start out with 500, and then it decays to 250. The amount of time to do that is called a half-life. Okay, they give us a chart here for these different substances. These are all isotopes. Carbon-14, you may have heard of that. They use that in carbon-14 dating. It has a half-life of 5,715 years. So they can find a fossil, they can figure out how much carbon-14 is in it, and they can figure, with mathematics, how old the bone is, or the fossil. Okay, so and then these other other substances I'm not as familiar with, cobalt-60, gallium-67, and then uranium-235. Okay, that has a really long half-life. Okay, so some have a quick half-life, like this one is only 80 hours, but most of them are in years here. Okay, now back to our formula. We have a model that says A equals A naught e to the kt, right? So we've had that model before, and we said A naught is the initial amount. How much you start with. Okay, but I want to go back and say, all right, how do you figure out this equation that we have over here? Well, when we're doing a half-life, we want to figure out a half-life, then the amount that we have at the end, so A, or they'll call it A of t, that's the amount after t time. So much time has passed, then that's the amount we have. And the little t is time. Okay. So in a half-life, you want half the amount of what you started with. Well, then you can divide both sides by A naught. So you just divide by A naught. And so you're going to get 1/2 equals e to the kt. Well, if you natural log it, you get the natural log of 1/2 equals just kt. And so that half-life is the k, all right? Okay, I think I might have said that wrong. So the half-life is the time, right? The time that it took. Now that's going to be capital T, that's going to be the half-life. So then you have the natural log, I'm going to make that 0.5 equals k times capital T. We'll divide both sides by the capital T, the half-life that you know, and then that's your constant that goes back in this formula that we have here, okay? And so hopefully that makes some sense. I need a little more room. Okay, so I may have scrolled when you weren't looking. Okay, so go back to your formula. A of t equals A naught e to the kt. But now we have a value for k. So A of t equals the initial amount, e to, and then it's going to be the natural log of 0.5 over t times little t. Okay, now we're going to rewrite that as e to the natural log of 0.5. Leave that like that. And then this will be t over, lowercase t over uppercase T, little t over big T. Okay. Then the exciting thing is this is just going to simplify to 0.5, which is 1/2. I'm just going to write it 0.5, and I'll change it in a minute. But that's where that formula comes from. So we have a formula now. It's written up at the top, but you're taking the initial amount times 1/2 to how much time you need, or how much time has gone by, over the half-life. So remember, capital T represents the half-life, and that we're going to find that on the chart for our problem that we're going to do. Okay, so now we're going to use that formula. How long will it take for 10% of a 1,000-gram sample of uranium-235 to decay? Okay, so first of all, what's 10% of 1,000 grams? Well, it's 100, right? So 10% is 100 grams. So we want the A of T to be 900. We want 100 grams to decay, and we want to know how long that's going to take. So find the formula. Okay, so we're going to have 900 equals, now what was the initial amount we started with? 1,000. And then you have 1/2. The little t, that's what we're trying to figure out, how long this is going to take. And then what's the half-life? Oh, I got to scroll up. I don't remember. It was a long number for the uranium. 703 million. Okay, I'll just write. I should put it in scientific notation. Okay, so I think that's what it is. Okay, so how are we going to solve this? Well, first you're going to divide by 1,000. That's right off the bat. So those are canceled. We're going to reduce that to 9 over 10. And then we're going to have 1/2 to the power of T over, I'm just going to write out the big number. Okay, and then what we'll do, because that little t that we're trying to solve for is up in the exponent, we're going to have to take the natural log of both sides. So we'll take the natural log of 9 over 10. And, well, I guess we don't have to do natural log, but we'll stick with the natural log. Whoops. I'm going to get rid of these fractions here in a minute. That long number. Okay, let's bring that exponent down in front of the natural log so we can do that. And I'm going to change those fractions to decimals, so it'll be easier to put in the calculator. Oh, I forgot to bring it down. Okay. So T over 703.80000 times the natural log of 0.5. Now remember, we want to solve for T. So go ahead and multiply by the giant number. And hopefully your calculator can handle that. It should be able to. And then now I have T natural log of 0.5. But remember, natural log of 0.5, that's just a number, so we're just going to divide by it. Okay, so we need to put all of this in our calculator. We're not going to do that by hand. Okay, so be careful with the parentheses. I'll talk you through it. So what I'm going to do is I'm going to put 703.8000000 times, and then I'm going to go natural log. Now, so I have this. I was just going to talk you through it, but I'll write it out. And then I went times natural log, and it opened a parenthesis, 0.9, and then I have to close that. Close that parenthesis. If you don't, it won't work. And then divided by, and then the natural log of 0.5. And what do I get? I get a very large number. I'm getting 106,979,777.2, but I'll just round it off, approximately that many years. Well, I wanted to double check it, but that seems like a lot of years to me. Okay, so that's how long it's going to take for 10% of the substance to decay. All right, that was a big problem.